will study solution of recurrence relation by method of generating function. In previous lectures, we have studied what are generating functions, how to find generating functions, how to find numeric functions related to generating functions. So today we will solve recurrence relation using the generating functions. So here I have written some numeric function and corresponding generating functions which we will use as a trial solution. Suppose AR is equal to 1, then AS is equal to 1 upon 1 minus S. AR equal to minus 1 raised to power n, then AS is 1 upon 1 plus S. If AR is alpha raised to power n, then AS is 1 upon 1 minus alpha S. We have also learned how to find these in the previous lectures. If AR is n plus 1, then AS is 2s upon 1 minus S square. If AR is n, then AS is s upon 1 minus S whole square. If AR is n square, then AS is s into s plus 1 upon 1 minus S whole cube. If AR is n, a raised to power n, then AS is alpha s upon 1 minus AS into whole square. If AR is factorial n, then AS is e raised to power s. If AR is c and r, then AS is 1 minus s raised to power r. Now how to find the generating function of the sequence a0, a1, a2, which is defined by this recurrence relation, which is an plus 2 an minus 1 minus 15 an minus 2 equal to 0, where n is greater than or equal to 2, with boundary conditions a0 equal to 0 and a1 equal to 1. We know that the generating function is as is equal to a0 plus a1s plus a2s square plus a3s cube and so on. This is the generating function. Now, and this is the given recurrence relation. An plus 2 an minus 1 minus 15 an minus 2 equal to 0. Here in the subscript we have n, here in the subscript we have n minus 2. So lower value of the subscript is n minus 2. So if we multiply this recurrence relation by s raised to power n on both sides and take the summation from 2 to infinity. For taking the summation, always take care of this subscript. Here it is n minus 2. So I have started my summation from n equal to 2 and up to infinity. If we multiply each term by Sn, then we get an s raised to power n, 2 an minus 1 s raised to power n minus 15 an minus 2 s raised to power n, and summation is taken from n equal to 2 to infinity, n equal to 2 to infinity, n equal to 2 to infinity. So if we substitute n equal to 2 to infinity here, we get a2 s square means this term, next will be a3 s cube means next term, then next will be a4 s4 next term and so on. So here we have the terms a2 s square onwards. So if we shift these terms to this side, we get as minus a0 minus a1s. So this series is equal to as minus a0 minus a1s. Now this is an minus 1 Sn. If we open this series, we will get for n equal to a1 s square. But here it is a1 s. a1 s square, next will be a2 s cube, next will be a3 s4 and so on. But here it is a1 s. So first of all we will take s common. If we take s common from this, then we will get a1s plus a2s square and so on. So first of all take s common here, then the series will be, if you shift this to this side, as minus a0. So this is as minus a0 as I have taken common. Now for the next term we have for n equal to 2, this is a0 s square. but here it is a naught. A naught s square, then we have a1 s cube, then we have a2 s4 and so on. So it means we need to take s square common, because it is a naught s square, a1 s cube, a2 s4 and so on. If we take s square common, then we will be left with the series a naught s square, a1s plus a2s square and so on. So take s square common, then we are left with the series as. So it is minus 15 s square as equal to 0. So here in place of this series n equal to 2 a n sn, we have as minus a naught minus a1s. In place of n equal to 2 to infinity a n minus sn, we have as minus a naught, and in place of a n minus 2 sn, we have s square as. Here it is multiplied by s. Now the boundary conditions are a naught equal to 0 and a1 equal to 1. Substitute a naught equal to 0, a1 equal to 1, a naught equal to 0. We get as minus s, because this is 0, this is 1. Here minus 2, this is s as minus 0, minus 15 s square as equal to 0. If we take as common, so if you take as common here, we are left with 1. If you take as common here, this is 2s. If you take as common, this is minus 15 s square, and this is minus s. Shift this minus s to right hand side, so this is s. It means as is equal to s upon 1 plus 2s minus 15 s square. If you factorize the denominator, we get 1 minus 3s into 1 plus 5s, because 5 3s are 15, minus 15s square, 5s minus 3s is 2s. Now we will decompose it into partial fraction, and we know how to decompose into partial fractions. Let this is equal to alpha upon first factor plus beta upon second factor. Here you can write a and b also. These hardly matters, because these are constants which we need to determine. So if you take LCM this side, it will be alpha into 1 plus 5s plus beta into 1 minus 3s. In the denominator we have 1 minus 3s into 1 plus 5s. This side also in the denominator we have the same term. So we can write alpha into 1 plus 5s plus beta into 1 minus 3s equal to s. Now we will find the values of alpha and beta by substituting the values of s. To find the value of alpha, we put 1 minus 3s equal to 0. If 1 minus 3s is 0, this term is 0 and s is equal to 1 upon 3. If we substitute s equal to 1 upon 3 here, it is 5 upon 3. 1 plus 5 upon 3 is 8 upon 3. So it means for s equal to 1 upon 3, 8 upon 3 alpha is equal to s is 1 upon 3, 1 upon 3. So 8 upon 3 alpha equal to 1 upon 3, it means alpha is 8. Now to find the value of beta, we put 1 plus 5s equal to 0. 1 plus 5s is 0 and s is minus 1 upon 5. If we substitute s equal to minus 1 upon 5 here, it will become plus 3 upon 5. 1 plus 3 upon 5 is 8 upon 5 and this is minus 1 upon 5. So 8 upon 5 beta is equal to minus 1 upon 5. It means beta is equal to minus 8. So if we substitute the values of alpha and beta here, alpha is 8, beta is minus 8, then as is equal to 8 upon 1 minus 3s minus 8 upon 1 plus 5s. So it means as is nothing but sigma n equal to 0 a n s n. So this is equal to 8 and this the corresponding series is 1 upon minus 3s means sigma n equal to 0 to infinity 3 raised per n s raised per n, and for this 1 plus 5s, it is plus here, so sigma n equal to 0 to infinity minus 5n s raised per n. See, AR equal to alpha n, then it is 1 minus alpha s. If AR is minus alpha n, then AR is 1 plus alpha s. So it is 1 minus alpha s, it is 1 plus alpha s. So alpha raised to power n means 3 raised to power n, and minus alpha raised to power n is minus 5 raised to power n Sn. So equate the coefficient of s raised to power n on both sides. Here we have an, here we have 8, 3 raised to power n, here we have minus 8, minus 5 raised to power n. And this is the required solution of the given recurrence relation. One more example. Now we will solve the recurrence relation an minus 7, an minus 1, minus 10, an minus 2 equal to 0 with boundary conditions a0 equal to 10 and a1 equal to 41. Similarly, as we did in first question, multiply each term by s raised to power n and take the summation from n equal to 2 to infinity, because here in the subscript we have n minus 2. So if we multiply each term by Sn, an Sn, minus 7, an minus 1 Sn, minus 10, an minus 2 Sn. Take the summation from n equal to 2 to infinity for each term. So like the previous example, an s equal to s raised to power n equal to 2 to infinity will be equal to as minus a0 minus a1s, because the series inside here is a2 s square, a3 s cube and so on. So shift these terms to this side, as minus a0 minus a1s. Here it is minus 7 and this is an minus 1 s raised to power n, means a1 s square plus a2 s cube and so on. a1 s square, a2 s cube, a3 s4. So first of all take s common, then inside will be a1s plus a2 s square plus a3 s cube. So s is taken outside, then the series is as minus a0. So this is as minus a0. Here if we put 2, a2 s square, sorry, n equal to a0 s square plus a1 s cube plus a2 s4 and so on. So a0 s square, a1 s cube, a2 s4 and so on. Take s square common. If you take s square common, then inside will be a0 plus a1s plus a2s square plus a3s cube, and this is as. So this is as here. Now take as common in these terms. So it is as, here it is 1, here it is minus 7s and here it is minus 10s square, minus 10s square. Shift the remaining terms to right hand side. This is a0, this is minus a1s, so this is plus a1, and this is minus 7s a0, so this is minus 7 a0 as I have taken common. It means as is equal to a0 plus s into a1 minus 7 a0, 1 minus 7s minus 10 s square. Now the given boundary conditions are a0 equal to 10 and a1 equal to 41. If we substitute a0 equal to 10 and a1 equal to 41, we get as equal to a0 is 10 plus s, a1 is 41 minus 7 into 10. 7 into 10 is 70. Means 41 minus 70 is minus 29. And in the denominator 1 minus 7 is minus 10 s square. Now we will resolve it into partial fractions. The factors of 1 minus 7s minus 10s square are 1 minus 2s into 1 minus 5s, because 5 2s are 10 and minus 5s and minus 2s are minus 7s. So it is LCM is 1 minus 2s into 1 minus 5s. So alpha into 1 minus 5s plus beta into 1 minus 2s is equal to 10 minus 29s. So it means to find the alpha, we put 1 minus 2s equal to 0, means s equal to half. So this term is 0, 1 minus 2s is 0, s equal to half means 1 minus 5 upon 2. 1 minus 5 upon 2 means minus 3 by 2. So this is minus 3 by 2 and this is 10 minus s equal to minus s equal to half. So this is minus 29 upon 2. So it means minus 3 by 2, 10 minus 29 upon 2 is 20 minus 29, means minus 9 by 2. Minus 3 by 2 alpha equal to minus 9 by 2. So 2 will cancel. So this will be alpha equal to 3. Now to find the value of beta, we put 1 minus 5 is equal to 0. So 1 minus 5s is 0 and it means s equal to 1 upon 5. So 1 minus 2 upon 5. 1 minus 2 upon 5 is 3 upon 5 beta minus equal to 10 minus 29 upon 5. So it will be 50 minus 29 will be 21 upon 5 and this is 3 upon 5. So it means beta equal to 7. So therefore we can write as equal to 3 upon 1 minus 2s plus 7 upon 1 minus 5s. So it means as is, we know that as is sigma n equal to 0 to infinity a n s n, and this is 3, this is 2 raised per n, s raised per n, here we have minus 5, so this 7, 5 raised per n, s raised per n. If we equate coefficient of s raised per n on both sides, we get a n equal to 3 into 2 raised per n plus 7 into 5 raised per n, and this is the required solution. Now we will solve the recurrence relation a n plus 2 minus 2 a n plus 1 plus a n equal to 2 raised per n with a naught equal to 2 and a1 equal to 1. Now here in the subscript we have n. So in this case we will multiply each term by Sn and take the summation from n equal to 0 to infinity. Always take care of this subscript. Earlier it was n minus 2, so we had taken the summation from n equal to 2 to infinity. Here it is n, so we will take the summation from n equal to 0 to infinity. So in this case, this will be sigma n equal to 0 to infinity a n plus 2 s raised per n minus 2 a n plus 1 s raised per n, sigma n equal to 0 to infinity, sigma n equal to 0 to infinity a n s raised per n, sigma n equal to 0 to infinity 2 raised per n s raised per n. So if we put n equal to 0 here, so it will be a2 s square, a2 s square plus a1 a2 s square, sorry, for n equal to 0 it will be a2 s raised per 0 is 1, so it is a2 plus for n equal to 1 a3 s, then a4 s square and so on. So here in the first term we have a2 a2, but with a2 there should be s square. Then we have a3s, but here it is s cube. So here earlier we were taking common, but now we will multiply each term by s square and divide each term by s square to get the values. If we multiply a2 plus a3s by s square, we will get a2s square plus a3s cube and so on, and divide by s square. Here I have written, so it will be as minus a naught minus a1s, as minus a naught minus a1s upon s square. Understand this step clearly, because for n equal to 0 we have a2 plus, because s raised to 0 is 1, so a2 plus a3s and so on, but here it should be s square and here it is s cube in place of s. So we have multiplied each term by s square and divided by each term by s square to get this series. So in that case it will be as minus a naught minus a1s upon s square. Now for this case, for n equal to 0 we have a1 s raised to 0 is 1, a1 plus a2s, but here we have a1s. Here we are getting a1 plus a2s plus a3s square and so on. So to get this series, we will multiply each term by s and divide each term by s. If we multiply each term by s, we will get a1s plus a2s square plus a3s cube, that will be equal to as minus a naught and this 2. So we have multiplied and divided by s. Now for this is n equal to 0. So this is a naught s raised to 0 is 1 plus a1s plus a2s square and so on. So these are the terms. So it is simply as. Here it is 2 raised per n s raised per n. So we know that for 2 raised per n it is 1 minus 2s. This we have done in first slide. These are standard. Also we know how to calculate these because we have learned these in first lecture. Now using the boundary condition a naught equal to 2 and a1 equal to 1. So if we substitute a naught equal to 2 here and a1 equal to 1, we get as minus a naught is 2, a1 is 1, so s upon s square. So s square I have multiplied each term by s square, so I have written s square here. So next term is 2 as minus a naught. A naught is 2. So here it was s because we are multiplying by s square. So s square upon s is s. Now this is as multiplied by s square and this is s square upon 1 minus 2s. We have multiplied each term by s square and substituted the values of a naught equal to 2 and a1 equal to 1. Now if you take as common here, here it is as. If you take as common, we are left with 1. Here if you take as common, we are left with minus 2s. Here if you take as common, we are left with s square. It means 1 minus 2s plus s square. 1 minus 2s plus s square is 1 minus s whole square. So I have written it directly, 1 minus s whole square. Shift other terms to right hand side. So this is 2 minus s and this is minus 2s into minus 2 minus 4s minus will be plus 4s minus s 3s, so this is minus 3s and this is s square upon 1 minus 2s. It means as is equal to 2 upon 1 minus s whole square minus 3s upon 1 minus s whole square s square upon 1 minus 2s into 1 minus s whole square. Again, I have written these steps directly because we can further simplify this to get the partial fractions because here we have two factors, but I have written all the terms directly because you know how to find the partial fractions now. So the series for this will be as equal to sigma n equal to 0 to infinity a n s raised per n. Here it is 1 minus 1 upon s whole square. So the series for this will be n plus 1 s raised per n. Here it is s upon 1 minus s whole square. This is 3. So series for this will be nsn and this is 1 upon 1 minus 2s. So series for this will be 2 raised per n sn. So I have used this because if this is 2s upon 1 minus s square, then this is n plus 1 If it is 1 minus alpha s, the numeric function is alpha raised to power n, and if it is 1 plus alpha s, then it is minus alpha raised to power n. So using this, I have written n plus 1 Sn. This is a corresponding numeric function. 3s upon 1 minus s square n Sn, and 1 upon 2s 2 raised to power n Sn. Now equate coefficient of s raised to power n on both sides. We get an equal to n plus 1 minus 3n plus 2 raised to power n, which is the required solution. Now an minus 2, an minus 1 minus 3, an minus 2 equal to 0, with a naught equal to 3 and a1 equal to 1. Multiply each term by s raised to power n and take the summation from n equal to 2 to infinity, because here in the subscript we have n equal to 2. So then this is equal to n equal to 2 to infinity an s raised to power n minus 2 an minus 1 Sn n equal to 2 to infinity n equal to 2 to infinity an minus 2 Sn. Now it is simple to write this series is equal to as minus a dot minus a1s. This series is equal to s into as minus a naught, and this series is equal to s square as, and this is minus 3 and this is minus 2 here. Now if we use the boundary condition a naught equal to 3 and a1 equal to 1, then we get as minus 3 minus s, because a1 is 1, then this is minus 2s, as, a naught is 3, then minus 3 is s square, as equal to 0. If we take as common, here it is 1, here it is minus 2s, here it is minus 3s square. Shift the other terms to right hand side. So it is 3, this is minus s, and this is plus 6s. 6, 3 2s are 6, minus minus plus. 6s minus s, 5s, so this is minus 5s. As is equal to 3 minus 5s upon 1 minus 2s upon into minus 3s square. If you factorize it, it is 1 minus 3s into 1 plus s. So you know how to find the partial fractions. Alpha upon first factor, beta upon second factor, and we can write alpha into 1 plus s plus beta into 1 minus 3s is equal to 3 minus 5s. To find the value of alpha, we put 1 minus 3s equal to 0, and alpha we get alpha equal to 1. For beta equal to to find the value of beta, we put 1 plus s equal to 0, means s equal to minus 1, and we get beta equal to 2. It means as is equal to 1 upon 1 minus 3s plus 2 upon 1 plus s. It means sigma n equal to 2 to infinity, Sn is equal to sigma n equal to 2 to infinity 3 raised to power n s raised to power n, sigma n equal to 2 to infinity minus 1 raised to power n s raised to power n. So equate the coefficient of s raised to power n on both sides. We get an equal to 3 raised to power n plus 2 1 minus 1 raised to power n, which is required solution. One more example, we will find the solution of an equal to an minus 1 plus 2 and an minus 2 and greater than equal to 2 for a naught equal to 2 and a1 equal to 7. If we multiply, the method is same for all the examples. First we multiply each term by Sn, then we take the summation depending upon the value of this subscript. So here it is n minus 2, so we are taking summation from n equal to 2 to infinity. All the steps are similar. Then we write the terms, simplify it, take the partial fractions, find the values of alpha and beta, and we get the generating function. And using the generating function, we write the solution of the recurrence relation. The step is same for all the theorems. So here it is, an is sigma n equal to 2 to infinity an s raised to power n equal to an minus 1 sigma n equal to 2 to infinity an minus 1 s raised to power n plus 2 an minus 2 sigma n equal to 2 to infinity an minus 2 Sn. So it means as minus a naught minus a1s is equal to s as minus a naught plus 2s square as. And this implies as is equal to a naught, this a naught plus a1s, and this minus a naught s. And if you take a as common, 1 minus s minus 2s square. So this is 1 minus s minus 2s square. If you put at a naught equal to 2 and a1 equal to 7, then we get a naught is 2 and a1 is 7. So 7s minus 2s. So this is 5s. Here it is 1 minus s minus 2s square. Factorize it. 1 minus 2s into 1 minus 1 plus s. So we will decompose it into partial fractions, alpha upon first factor plus beta upon second factor, and we will write it as alpha into 1 plus s plus beta into 1 minus 2s equal to 2 plus 5s, because in the LCM is 1 minus 2s into 1 plus s. So alpha into 1 plus s, beta into 1 minus 2s, and in the denominator we have the same terms, so I have written directly alpha into 1 plus s plus beta into 1 minus 2s equal to 2 plus 5s. Now to find the value of alpha, we will put 1 minus 2s equal to 0, means s equal to half. To find the value of beta, we put 1 plus s equal to 0, means s equal to minus 1. For s equal to 1 upon 2, we get alpha equal to 3. For s equal to minus 1, we get beta equal to minus 3. It means generating function as is equal to 3 upon 1 minus 2s minus 1 upon 1 plus s. So I have written the solution of given recurrence relation directly. Skip the one step. I have skipped one step. 3 2 raised to power n minus 1 raised to power n, because the series here will be sigma n equal to 2 to infinity a n s raised to power n, and this will be 3 sigma n equal to 2 to infinity 2 raised to power n Sn, and here it will be minus sigma n equal to 2 to infinity minus 1 raised to power n s raised to power n. So we have equated the coefficient of s raised to power n to write a n equal to 3 into 2 raised to power n minus 1 raised to power n. One more example, a n equal to 3 a n minus 1 plus 2. Here in the subscript we have an a n minus 1. So multiply each term by Sn and take the summation from n equal to 1 to infinity. So here it will be n equal to 1 to infinity a n Sn. So it is 3 n equal to 1 to infinity a n minus 1 Sn plus 2 n equal to 1 to infinity s raised to power n. I have multiplied each term by Sn and taken the summation from n equal to 1 to infinity. If you put n equal to 1 here, so it will be a1s, means this term a1s. Then next term is a2s square, means this term. Next will be a3sq, means this term. So these are the terms we obtained in the first case. So we are left with as minus a naught. So this is as minus a naught. For the second case, we get n equal, if we put n equal to 1, we get a naught s plus a2 s square. Sorry, a1 s square plus a2 s cube and so on. But here we have a naught, not a naught s. So take as common. If you take as common, we are left with a naught plus a1s plus a2s square and so on. So take as common, inside we have as. Here it is the term as, bracket is a typing mistake, it should be a, then s is inside the bracket. And for here this is 2 and this is s raised to power n. If this will be for n equal to 1 s plus s square plus s cube and so on. In fact, it is a infinite geometric series. First term is s and common difference is s. So s upon 1 minus s, because sum of infinite series is a upon 1 minus r. So s upon 1 minus s. Take a as common. So it is 1 minus 3s and shift this to this side. A naught, but A naught is 1, so I have written it 1 plus 2s upon 1 minus s. So it means as equal to 1 plus s means 1 minus s plus 2s. So it will be 1 plus s, and this 1 minus 3s, and this 1 minus s. Now resolve it into partial fractions. Alpha upon first factor plus beta upon second factor. So it means alpha into 1 minus s plus beta into 1 minus 3s is equal to 1 plus s. Now to find the value of alpha, we put 1 minus 3s equal to 0, means s equal to 1 upon 3. To find the value of beta, we put 1 minus s equal to 0, means s equal to 1. For s equal to 1 upon 3, we get alpha equal to 2. For s equal to 1, we get beta equal to minus 1. Therefore, the generating function will be as equal to 2 upon 1 minus 3s minus 1 upon 1 minus s. So it means this is n equal to 1 to infinity a n s raised to power n. This will be 2 n equal to 1 to infinity 3 raised to power n s raised to power n equal to 1 to infinity s raised to power n. So equating the coefficient of s raised to power n, we get a n 2 3 raised to power n minus 1 for n greater than equal to 1. This is the solution of the given recurrence relation an equal to 3 an minus 1 plus 2. Now one more example. To find the solution of an equal to an minus 1 plus an minus 2 with a1 equal to 2 and a2 equal to 3. Here a naught is not given. Therefore, the recurrence relation is not valid for n equal to 2. Because if you put n equal to 2 here, we get a naught. But a naught is not given to us. And it is valid for n greater than equal to 3. But if we put n equal to 2 here, we get a2 equal to a1 plus a naught. And we know that a2 is 3 and a1 is 2. So 3 minus 2 is a naught, means a naught is 1. So if we choose a naught equal to 1, then this recurrence relation will be valid for n greater than equal to 2. So in this case, then we can multiply it by Sn, s raised to power n, and take the summation from n equal to 2 to infinity. So it will be n equal to 2 to infinity an s raised to power n equal to 2 to infinity an minus 1 s raised to power n equal to 2 to infinity an minus 2 s raised to power n. We know that this is as minus a naught minus a1s. We know that this is s into as minus a naught, and this is equal to s square as. So if we take as common, we get 1 minus s square, and shift other term to this side. A naught is 1 and a1 is 2, so this is 2s, and this is s a naught. So a naught equal to 1, so s. So 2s minus s is s. So 1 plus s upon 1 minus s square. We know that we cannot factorize it, means the value of s will be equal to the value of s can be obtained by Sridharacharya method, and it will have two roots, 1 plus under root 5 upon 2 plus beta equal to 1 minus root 5 upon 2. Because if ax square plus bx plus c equal to 0 is the equation, then x is equal to minus b plus minus b square minus 4ac upon 2a. Applied that method, then in that case one root will be 1 plus root 5 upon 2, another will be 1 minus root 5 upon 2. So I have written alpha and then another root to be beta. So factor of this can be written as 1 minus alpha s into 1 minus beta s. It means as is equal to, if we resolve it into partial fractions, we will get 1 plus beta upon alpha minus beta, 1 upon alpha minus s plus 1 plus beta upon beta minus alpha, 1 upon minus beta s. The method of finding the partial fraction is same, means a upon first factor alpha, because we are using alpha here, so we can write a upon first factor a upon 1 minus alpha s plus b upon second factor b upon 1 minus beta s, and find the values of a and b as we have discussed in previous example. In that case, we will obtain a equal to 1 plus beta upon alpha minus beta and b equal to 1 plus beta upon beta minus alpha. So this is obtained by decomposing it into partial fraction. So it means as is equal to 5 plus 3 under root 5 upon 10 into 1 minus alpha s whole square. I have substituted the values of alpha and beta. In this case, beta is 1 minus under root 5 upon 2 and alpha is 1 plus under root 5 upon 2. If you substitute the values of alpha plus beta here, alpha and beta here, you will get 5 plus 3 root 5 upon 10. Similarly, in this case, minus 5, 3 under root 5 upon 10. And this is 1 minus beta is raised to power minus 1. It means the solution will be an equal to 5 plus 3 root 5 upon 10 alpha raised to power n and minus 5 3 root 5 upon 10 beta raised to power n. This is obtained by equating the coefficient of s raised to power n on both sides. But we know that alpha is 1 plus root 5 upon 2 and beta is 1 minus root 5 upon 2. So this will be 1 plus root 5 upon 10, 5 upon 2 whole raised to power n, and this is 1 minus root 5 upon 2 whole raised to power n. So this is the solution of recurrence relation, this. In fact, this is the Fibonacci sequence. An equal to an minus 1, an minus 2. So these are some standard recurrence relation, means like Fibonacci sequence, Padovan sequence, Lucas sequence, Pell sequence. These are some standard examples. Thank you.